I will begin
Want me to do the camera?
with a, oh, that'd be awesome, with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. I pray for the other ones to travel here safely in the following minutes. Lord, in your name I pray. Amen. All right, so in the interest of not going late, those who are not here yet can watch this later. Today, we're going to talk about the real Jordan form. And complexification. So, why do we need to talk about this? What's the shortcoming of just Jordan form? Well, the trouble is, if we have a linear transformation from a real vector space on a real vector space, right? If we have T is linear transformation from V to V, where V is vector space over R, then it may be that the characteristic polynomial equals to 0 has no real solutions, right? In other words, is it okay? Is it working? Oh, I'm sorry. So it has no real solutions. In other words, no eigenvalues, right? Or even if it has some eigenvalues, or possibly not enough. Not all real solutions, right? I mean, so if your linear transformation or your matrix gives you a characteristic polynomial where it doesn't factor over the real numbers, then we can't apply the Jordan form technology because our eigenvalues are not in the field. But why is this not a problem for complex numbers? Like, what if instead of having a transformation over vector space, a transformation of a vector space on the real numbers, what if instead we have a transformation of a vector space over the complex numbers? If we had a linear transformation, say S, going from a vector space over the, let's say W, to W over the complex numbers, then if we look at the characteristic polynomial of S, right, which was what? This was the determinant of S minus X, right? This is a nth order polynomial, all right? Right, with coefficients in C. And what do we know? The fundamental theorem of algebra tells us that if we look at an nth order polynomial equation in the complex numbers, we can solve it, right? There exist n complex solutions. Here I'm supposing that the dimension of W is n. So that situation would say what? I mean, if we're looking at a linear transformation of the complex numbers, then we're in business because the characteristic equation will have eigenvalues, right? Which implies that the characteristic equation has n solutions, possibly repeated. All right, and we call those lambda 1, lambda 2, lambda n. Right. So if we have a linear transformation on a complex vector space, then we don't have this deficiency right? A real linear transformation, it doesn't have to have all of its eigenvalues in the field, right? So, do you guys understand the problem? Does this make sense? I mean, it's advantageous to us then if we can take a given real linear transformation and somehow convert it to a complex linear transformation, because if we could do that, then we can apply the Jordan form, at least in principle, to what's in red and kind of work our way backwards to some sort of quote-unquote canonical form for such a case. The sum total of this idea is encapsulated in what I call the real Jordan form. The real Jordan form is not technically a Jordan form. It's a related but different pattern you can put the matrix into, which uniquely tells you, for example, two matrices are similar if and only if they have the same real Jordan form up to repeating of the blocks. So for those of you who just came in, I haven't really done anything. Yeah.
Are you saying that it doesn't work over the reals, like there's no eigenvalues because you get a zero vector?
Example. If we had A equals to, say, 2 minus 3, 3, 2, then the determinant of A minus lambda I, well, I'll tell you, I'll use the x, right? Determinant of A minus xi, which would be the determinant of 2 minus x minus 3, 3, 2 minus x. So you work that out, you've got x minus 2 quantity squared plus 9, right? That's irreducible. This is an irreducible real polynomial. There are no real solutions, right? Okay, so on the other hand, if I could somehow look at that as a complex equation, we'd be in business, right? Because if you allow yourself to have, complex numbers, then you can factor this, right? How does it factor over the complexes? Don't worry, we really haven't done anything yet. All right. So, I guess I'll kind of start class now. Let's look at the complexification. So the complexification is going to help us with this problem. So let V be vector space over the reals, then construct V sub C. It's going to be V cross V, the Cartesian product of V and V, all right, with the addition of vectors as usual. How do you add vectors in the Cartesian product of V and V? You just add components, all right? We've done this before, but I'm going to make this an honest-to-goodness complex vector space as follows. We're going to say A plus IB times x comma y, all right? And this is the definition. I'm going to show you how to make V cross V into a complex vector space. We already know how to add vectors because we just add pairs by adding components. All that I need to do is give you a way to multiply a complex number on this pair. How do you do it? You do it like this. ax minus by, comma, ay plus bx. This defines a scalar multiplication on v sub c. All right. So let me introduce an easier notation. So an easier notation here, rather than saying x comma y, if we say x comma y is x plus iy, so use this notation, x plus iy, then in that notation, if you look at a plus ib times x plus iy, what does it work out to? What's this up here? So I'm saying in this notation, it's ax minus by plus I times ay plus bx. How's that go? So basically, I'm just saying that the I in the scalar, a plus ib, interacts with the I in the vector, iy, such that I times I is -1. That's where this definition came from. It's basically just to make this happen. All right? But you should understand, I'm not just, making something that's not well defined. I mean, it's a Cartesian product of v and v. We can do this. And that's the definition of the scalar multiplication. So the complexification is a specific thing. It's this. All right? Now, so then, given T, a linear transformation from v to v, right? I can also define the complexification of T. T sub c, which will be a mapping from v sub c to v sub c, is given as follows. T sub c of x plus iy is equal to, what should T sub c of x plus iy be equal to? This is the definition of complexification of a linear operator. All right. So it is a unique corresponding complex linear operator that acts on the complexification. In this way, we can achieve the goal which I was saying at the start. We can start with a T, which is a real transformation, and build a corresponding complex transformation by just putting S equal. Basically, I'm just endorsing the idea we put S equals to T sub c, and we put W equal to V sub c. Like that is the trade we're going to make. We're going to trade our given transformation for the complexification. Listen, we do this all the time in differential equations, and we don't even admit that that's what we're doing. All right, let me show you an example of this. So, solving something like y prime prime plus y equals to 0. If that's a real differential equation, okay, I can say extending to complex case, complex y, or extending to complex. So say trade my y for a z. The corresponding complex problem is z prime prime plus z equals to 0. Here z prime is dz dt. All right? And if you have some background in complex analysis or just calculus too, really, notice that z equals to e to the it, right? Z equals to e to the it is what? It's a solution, right? Because z prime is I squared e to the it, which is minus e to the it, right? Which is equal to minus z. Therefore, z prime prime plus z equal to 0. But that's not a solution to the original problem. The original problem was for a real y. This is I mean, I'm assuming at the start of this that, y is some kind of mapping from the reals to the reals. So the given problem is a real differential equation. I extend the differential equation to a complex differential equation where I can naturally solve it. Yeah? That's a complexification. And this is something, it's a technique we can generally use on a real problem. We can complexify it. All right? So, and in this case, I worked this out in calculus 2 the other day. This is actually cosine t plus I sine t, right? And in fact, the cosine t and the sine t are both separately real solutions to the original problem. Right. I'm not going to get into the mechanics. This is differential equations. I'm not going to get into the mechanics of that here right now. It's not really, this is just illustrative of the idea. It's not just something I'm doing in linear algebra. This is a more general technique which we use. My point is that it's not just hocus pocus, like, oh, we'll complexify the problem, like that even makes sense. Yes, it does make sense. There's a well-defined procedure for taking a real problem and changing it into a corresponding complex problem, such that the new complex transformation is like intricately linked to the original real transformation. Okay, so let us study this problem then. We'll start with a 2-by-2 case. So consider the case that t is a linear transformation from v to v, where v is two-dimensional over R, right? And suppose that the characteristic, well, suppose that the determinant of t minus x works out to x minus alpha squared plus beta squared. What would this mean? There does not exist real solutions, right, to the determinant of, if it's okay with you guys, I'm going to use a lambda instead of an x here. Forgive me for that. Right. Okay. All right. So in this case, it's interesting to study the complexification of t. All right. Let's look at further. Let's suppose v is equal to the span of, let's say, v1 and I don't want to do that. This is not helpful. Let me stop that. So sorry. All right. So what I want to prove for you is that the complexification of t has the same characteristic equation, among other things. Let's see here. So what would the complexification of v in this case be? T sub c of, x plus iy is equal to what? T of x plus I t of y, right? And let's study what it means so I have a hunch, right? I have a hunch that the complexification, here's my hunch. Let's go from this perspective as an educated guessing rather than my other path I was thinking about going down. So what I've already calculated gives me a very strong suspicion that the complexification has eigenvalue what? It's a complex eigenvalue. That makes sense for the complexification because it's a complex linear operator. It can have a complex eigenvalue. What do you think we suspect? Suspect what? I suspect that lambda equals to alpha plus or minus I beta are complex eigenvalues for T sub c. How can we check that? Maybe I've started us out on the wrong foot. Maybe I should ask a slightly different question. Suppose the complexification of a given transformation has complex eigenvalue, alpha plus or minus I beta, all right? Then what does that say for the underlying real transformation? We can look at that. So if this is true, what does that mean about T sub c? That means that T sub c times some vector, let's call it v, is equal to what? Alpha plus I beta times v for v not equal to 0, right? So there exists such a v if there is, in fact, the complex eigenvalue of alpha plus I beta. Agree? I mean, this is the definition of complex eigenvalue. But let's see here. Moreover, v we could write as v1 plus I v2. Actually, I'm going to use my usual notation, which is a1 plus I b1. Excuse me. I'll eventually get it. A plus IB, because there's no number on the V. Later I put like a V1, then I'll have an A1 and B1 and so forth, all right? But there's no number on the V, so let me just use A plus IB. That's my typical notation here. What is that? What is T sub C on A plus IB equal to? By definition, T of A plus I times T of B, where T is the underlying transformation we're complexifying. All right, that would be equal to alpha plus I beta times A plus IB. But we know how to multiply. It just multiplies out in the natural way. You're like, you just told me about this complexification like 3 minutes ago. How am I supposed to already know how to work in it? It's the same as what we've been doing. It just works. It's not complicated. It really isn't. Just remember I squared equals to minus 1 and proceed normally. Oh, look at this. look at this. So this is why, if we have a complex eigenvector for the complexification, it gives us information about the original transformation. Why? If I go back to the blank comma blank notation for this, right? If I go back to the v cross v notation at this point, what this equation says is that t of a comma t of b is equal to alpha a minus beta b comma beta a plus alpha b. Because I'm just writing the real and imaginary components of this vector equation. But if you have a pair of things equal, what does that mean? Definition of Cartesian product means each slot has to separately match, right? In other words, the real part has to match the real part, the imaginary part has to match the imaginary part. And so that gives us the equality of TA with that and TB with that. What does that tell us? That tells us that if we look at the complexification of a real transformation on a two-dimensional space, and it just so happens that that transformation has a complex eigenvector of a plus ib. So I'll rewrite it. We have if Tc of a plus ib equals to alpha plus I beta times a plus ib, then we have two things. We have that T of A is equal to alpha A minus beta B, and we also have that T of B is equal to beta A plus alpha B. Here A and B are vectors in V, all right? So the existence of an eigenvector for the complexification has given us this information about the underlying real transformation, right? And what does that mean? If you look at if we set, let's say, gamma equal to a comma b, I would usually use basis beta, but that seems like a bad choice here, right? Yeah. So with respect to basis gamma, what's the matrix of T gamma gamma? You can read it from right up here. It's alpha minus beta, beta, alpha, I think. Let me double check on that. Let me not skip steps. I'll it's probably healthy for you guys to see this. This should be the T of A gamma coordinates, right? Then T of B, the gamma coordinates of that. That's how we calculate the abstract matrix, right? What's the coordinate of T of A with respect to the gamma basis? Alpha minus beta, right? What's the coordinate of T of B? It is beta comma alpha. Now I've forgotten my notation. Let me see if I can find it right quick. Oh, this is exciting. I have no notation. You know what that means? That's right, we get to do our own name calling. Let's see here. You guys are all Trump supporters. You like name calling, right? Do I have to edit? Do I have to edit that? I mean, I'm fine. I mean, let's admit it. I mean, if you voted for him, you're probably happy that he calls people names, right? I mean, come on. I mean, it gives me joy. I was so hopeful for late night comedy during the Trump administration. They've gotten so angry, though. Like, I was looking forward to like 4 years of genuine, well-deserved comedy. But they're just mean and angry. It's no fun. Oh, well. Okay. So I need a notation for, I mean, this, I don't know. For lack of a better notation, I'll say this is the real Jordan form of 2 by 2 alpha plus I beta. Real Jordan form. Maybe I should put a 1 there, maybe then I'm going to put a 2 there because it's a 2 by 2 block.
Okay.
Let's go with a 2 to match the size of it. It does correspond to just one complex eigenvector, though, doesn't it? Do you notice my example? I erased it. Aw, man. If you can go back in time, you guys took notes. What I had written here was what?
Don't remember.
A.
Yeah.
So that's the real Jordan form of what? Two minus 3i, yeah. And by the way, this I would call a quote-unquote real Jordan basis. So if the matrix is already in real Jordan form, that means that the standard basis is a real Jordan basis. And if you think about this discussion and track back, that means that V equals to E1 plus IE2 is complex eigenvector with lambda equal to 2 minus 3i. In other words, you can check that A times 1i is equal to 2 minus 3i times 1i. This is true.
So you're saying that if we check by row reduction, E is equal to E1 plus I2. Is that what you're saying?
Ah. So now you're starting to ask the question, how do I actually find these, right? Yeah, yeah. Well, I think it's best for us to look at the projector here on those. Oh, before I do though, one last thing. What is this kind of matrix mean? Well, if you look at this as 1 over alpha squared plus beta squared, excuse me, if you look at this as alpha squared plus beta squared square root, and then we've got alpha over square root alpha squared plus beta squared, beta over square root of alpha squared plus beta squared, minus beta over square root, I'll get out of the way here in a second, alpha squared plus beta squared, alpha over square root of alpha squared plus beta squared. That.
What? Why are you doing that?
I know, right? Why?
Can we not do that?
Because then if you look at this matrix R, if you look at that matrix R, you can prove that that has the property R transpose R equals 1, 0, 0, 1. And also you can prove that if this, you can identify alpha equals, you can identify alpha over the square root of alpha squared plus beta squared as being cosine of theta. You can identify beta over the square root of alpha squared plus beta squared as being the sine of theta, which makes R a rotation by angle theta. Well, conceptually, you might ask, what does it mean geometrically when a 2 by 2 matrix has a complex eigenvalue? The answer is, it's a combination of a dilation and a rotation. Dilation in the front is multiplication by this constant factor, and this is some sort of rotation. That's what a matrix with a complex eigenvalue corresponds to, some sort of dilation, which is either a expanding or a contracting of space, and then a rotation. That's what that is. We'll talk more about rotation matrices later in the course. It's not something you're supposed to already know about, okay? So this is a forward-looking comment. That's all. So, pragmatically speaking, the question that you should ask is, how do I find, and when do I need to find the real Jordan form of a matrix? What's the answer to that question? When do we need to, when would we want to find the real Jordan form of a matrix? That would be when some of the eigenvalues are not real. If we have a complex eigenvalue, and how do you define if there's a complex eigenvalue or not? Well, the good news is, and although I haven't proved it today, it can be proved, that the characteristic equation of the complexification and the characteristic equation of the original transformation, they are one and the same. So, you have already calculated the characteristic equation of the complexification as soon as you calculate the characteristic equation of your original matrix. And it's really, really simple. You just ignore the fact that your original problem was real and treat it as if it's complex. And that's how you find complex eigenvectors. You just take the real matrix and think of it as a complex matrix and find the eigenvectors with respect to complex numbers. It's the same calculation we've already been doing, it's just you get a complex answer. Then what do you do with it? Well, you pick it apart into real and imaginary parts to construct a Jordan basis, and that gives you a Jordan block for the original problem. This is the finding of the Jordan form. Here, I have an example. I'll show you. So there are some nuts and bolts here I have, glossed over. In particular, that if you have a basis for your, there's an interplay between the basis for the complexification and the basis for the original vector space and vice versa. There's another question. How did I know A and B were linearly independent in the abstract derivation? It can be shown that if you have a complex eigenvector that's stemming from a genuinely complex eigenvalue, in other words, alpha plus I beta, where beta is non-zero, that implies that A and B are linearly independent real vectors. That's something that I show in the notes. There, of course, are some other sort of nicer things I should have said along the way that, for some reason, I was slightly angry today. Earlier on, I don't know why I would possibly be angry. But it's a little too bright. There we go. So, the complexification of the real numbers is the complex numbers. This thing I showed you is a construction of the complex numbers as the real plane. All right. If you apply the construction that we looked at to Rn, you can construct Cn. You can construct n by n complex matrices by doing this. That's weird. That showed up. This is really strange. Oh, it's the cursor. Curse the cursor. There we go. All right. Ah, no! Oh, dang it. Oh, yeah. Oh, man, we're all the way back to quotient spaces. Nobody wants to see that. You don't want to see any of it. Hurt me with that. Ah.
I have 235 actually. Yeah, that's a picture of 235.
All right.
Oh, wait, no.
Thank you. I was trying to get to an example. All right. Another thing that's worth mentioning is if we're looking at the complexification of a real transformation and we find an eigenvector z, then the complex conjugate of that eigenvector, which for us, if we take a plus ib and convert it to a minus ib, guess what? That's also a complex eigenvector for the complexification with complex eigenvalue conjugate of what we had. So that's what this calculation shows, that the complex conjugate of the eigenvector has eigenvalue complex conjugate of the original eigenvalue. So that's neat. The complexification also has complex eigenvalues that come in conjugate pairs. This is not surprising to us if we think about the fact that I told you they have the same characteristic equation, right? The characteristic equation for a real transformation is a polynomial with real coefficients. If it has a complex solution, they come in conjugate pairs, right? They have to. This is algebra. And so we just derived theorem 8.3.15 somewhat carefully. There it is. If you had a bunch of these, all right, suppose you look at the complexification of a matrix and you had not just one complex eigenvector. Suppose you had a bunch of them, Vj plus Aj plus Ibj, and each one of these was a complex eigenvector for A with eigenvalue alpha plus I beta j, where beta j is non-zero. Then if you do a similarity transformation by the real Jordan basis formed by stringing out real imaginary, real imaginary, real imaginary, real imaginary of your complex eigenvalues, vectors rather, then you get a direct sum of these real Jordan blocks. It's just like those 2 by 2 blocks down the block diagonal. It's not diagonalized, but it's close to it. It's almost diagonalized. It's as good as we can do. But you might, when you look at the complexification, not that would be in the case that the previous one I just looked at would be when the complexification was diagonalizable as a complex transformation. We have learned this week, I hope, that not all transformations are diagonalizable. Sometimes you need the generalized eigenvectors. So what does that mean? If your complexification needs generalized eigenvectors, in other words, you have an eigenvector v1 and you have a generalized eigenvector v2, where so like the complexification minus lambda v2 is equal to v1. So v1 and v2 form a 2-chain of complex eigenvectors for the complexification. In that case, when you look at I would call this the real Jordan basis, a1, b1, a2, b2, you get this kind of funny, you get the 2 by 2 blocks that we've already seen, and it puts a 2 by 2 identity matrix up here. That's what happens. This is a lot like the pattern we saw in that test problem with the 1, 2, 3, 4 matrix. It's kind of like that. There's the proof is there. It's not especially exciting. If you had a transformation on a 6-dimensional space and it only had the complexification only had one complex eigenvector with a complex eigenvalue 3-peated, then there would be 3 conjugate pairs, and this would be the complex Jordan form, J3 lambda, direct sum J3 lambda bar. This would be the matrix of the complexification with respect to the natural Jordan basis over there. When you take this delta basis and you look at its real and imaginary parts, it brings you back to a 6 by 6 real matrix. This is the 6 by 6. I would call this, I guess the notation for this would be Rj sub 6 of alpha plus I beta. That would be the notation I'm suggesting we use for that to be consistent with the thing we just said there. There's a cool way to write these formulas more compactly. You could write this. This is the tensor product. So the way this works, guys, if you have the tensor product of this matrix and this matrix, you just take this, multiply it by 1, and put it up here. Chunk. You take this, multiply it by 0, put it up here. It's not even here. This is not from this one. You take this, multiply it by 0, put it over here. That's that 0. Take this, multiply it by 1, put it here. So this piece and this piece are coming from that. This over here, you take this, multiply it, it gives you 0, and this chunk, this chunk, this chunk, and it puts an identity up here. It's exactly that. So this is a way of building the formulas with something called the tensor product. So the 3 by 3 one looks like this. And I don't even have, I don't want to write this out. This is an 8 by 8 matrix, but the pattern, if you use the tensor product, the pattern becomes clear. Now, you probably don't understand what I'm saying entirely at the moment, and that's okay. There are homework problems. Once you work those, you'll know what I want you to know about it, okay? Here is a specific problem. If we look back at example 8.1.26, which was basically to look at the eigenvectors, I think, of this matrix, 1, 1, 0, minus 1, 1, 0, 0, 0, 3, all right? That matrix had only one real eigenvalue. The real eigenvalue was 3. The complex eigenvalue of this matrix in the middle is 1 plus I. How do I know that? I can see it by inspection, see, because this matrix is already in real Jordan form. This is RJ2, 1 plus I. See, I'm alpha equals 1, beta equals 1. Yeah? Right? Yeah? Okay. So anyway, and then that's a J13. So if the matrix is in block diagonal form where each one of the blocks is either a Jordan block or a real Jordan block, I can read from each one of those blocks what the eigenvalue and also the algebraic and geometric multiplicity if I think about it. Anyway, so eigenvector, this is a complex eigenvector. This is the conjugate of that, which is the eigenvector with the complex conjugate eigenvalue. This has perhaps 1 plus I. This has eigenvalue 1 minus I. That has eigenvalue 3. When you do a similarity transformation with respect to the basis matrix, what do you get? You get, well, it diagonalizes it over the complex numbers. Right? So the complexification of this matrix can be diagonalized. The matrix itself cannot be diagonalized because it has a complex eigenvalue of 1 plus I and 1 minus I. The matrix can only be diagonalized over the reals if all of the eigenvalues are real and the whole space is the direct sum of the eigenspaces, which is to say that there exists an eigenbasis. Here's the calculation I rattled off on the board with a smarter choice of notation. Set R equal to the square root of... Now, also, there's a danger here. This A is my alpha. The B is my beta. The calculation I have covered up has A and B as two-dimensional vectors, right? So, yeah. Let's see here. Have you guys learned enough to tell me what are the... oh, don't read this. Don't read this. Ah! Dang it. So this is the real Jordan block with complex eigenvalue 2 plus 3i. And this says that you have real eigenvalue 5, geometric multiplicity 1, algebraic multiplicity 2 for eigenvalue 5. Because we have a 2 by 2 Jordan block, which means there's just one eigenvector and one generalized eigenvector. So the algebraic multiplicity is larger than geometric multiplicity. This one would tell me I have complex eigenvalue plus or minus 3i with algebraic multiplicity 2, geometric multiplicity 1. This is J4. This is J4 of 3i. RJ4 of 3i. RJ4 of 3i in our current lingo. And look down here. This tells me that the eigenvalue 5 has geometric multiplicity 2 because there's two eigenvectors. The eigenvectors are E5 and E6. I can read that from this. Anyway, long story short, for any real matrix, there exists a real Jordan form, which is understood to be the direct sum of real Jordan blocks. To transform into that, you find the real Jordan basis and similarity transform. Two real matrices are similar if and only if they have the same real Jordan form up to reordering of the blocks. That's general. I can't say the same for Jordan form because many real matrices don't have all their eigenvalues. But every matrix has all of its complexification of any matrix always has all the eigenvalues because it's complex. So anyway, I now leave you to your homework. Have a good weekend. Ooh, polynomials and operators. That is this. You can tread lightly on this section. This section's got some hard stuff in it.